Hello, ladies and gentlemen. Today we are going to finish up parts of that foldable here on different factoring methods that we haven't talked about up to this point. So you need those notes. We're going to write those in there again, as well as something to write with and possibly a calculator. So remember this little foldable, we've talked about what it means to factor, we've talked about greatest common factoring, as well as group factoring, the thing we do when we have four terms. Well, not everything we need to factor has four terms. Sometimes it has three terms or three pieces or two. So what do we do in those situations? We can go ahead and take a look at these two different methods today called trinomial factoring, which is called the AC method, and difference of perfect squares. So let's first take a look at that trinomial factoring page. If you'd open that one up, these are the steps that we're going to go through when we do trinomial factoring or factoring on things with three terms. So to set this up, we're going to use what's called the AC method. You take the A coefficient times the C constant of the problem. Then you ask yourself what multiplies to make that number and will add up to the middle term. So we're going to look for two numbers that multiply to make that number, but add to also make the middle term of the problem. And once we have that question answered, then we can turn that three-term problem into a four-term grouping problem, and we can revert back to that factor by grouping method the page before. So let's take a look at three examples here. Each of these has three terms. So remember, three terms is indicated there by all the pieces that are being added or subtracted together. So because this problem has three terms, an x squared, a 7x, and a 6, it's a trinomial. We can't just go straight to that grouping method as it is right now, but we can do this AC method to get it looking more like a grouping problem. Let's take a look at what that would look like. So let's follow these directions. We're going to take the A coefficient times the C constant. Now, you might remember back from Algebra 1, you always wrote these as ax squared plus bx plus c. A trinomial, that is a quadratic. These A, B, and C represent the coefficients or the numbers in the problem. The A is in front of the x squared, the B is in front of the x, and the C is the constant at the end. So if I need to take the A times the C to follow these directions, the A would be the number in front of the x squared, which would be 1, and we're going to multiply that times the C in the back. So we're going to take 1 times 6, and that gives me the number 6. Now, once I figure out what that is, the A times the C, then I got to ask myself a critical question. What multiplies to make that number, the number 6, and will add to make the middle term in our problem? So I need to ask myself what multiplies to make 6 and will add to make 7, that is the middle term in my problem. So that answer, these are the things that multiply to make 6. 1 times 6, 2 times 3, negative 1 times negative 6. Remember, negatives, two negatives multiply to make a positive. And negative 2 times negative 3. But I'm looking for the pair that will add to make 7x in the middle. That's these guys, 1 and 6. Once I decide what actually makes 7, then I can turn this three-term problem into a four-term grouping problem. Check this out. I'm going to rewrite this problem as the x squared and the 6 at the end, but in the middle, 7x's is equivalent to 1x plus 6x's. Where did I get the 1 and the 6? From the list over here. So I rewrote this three-term grouping problem or three-term problem into a four-term grouping problem that we can now do that grouping strategy to. So that, remember, is partner the first two. What's something common I can divide out of those? I can take an x out of both of those. That would leave me with an x plus 1. What can I divide out of both of those terms? They both have a positive 6. So I'll place the 6, and then we'll have x plus, remember, 6 divided by 6 is 1. So I know I'm going to have these two factors. One of them is going to be x plus 1 because I can factor out x plus 1 from both terms now. And what would be left is the x plus 6. So this trinomial factors into these two pieces or binomial pieces that would multiply together to make this. So we're undistributing the process here. We're taking away what was distributed so we can see what was in fact multiplied to make this problem. Okay, let's try another one. Example 2. A times C. So beginning is a 1 times the end, negative 16. 1 times negative 16 is negative 16. So we're asking ourselves, what multiplies to make negative 16? Well, there's lots of things. There's 2 and negative 8. There's negative 2 and positive 8. There's negative 4 and 4. There's negative 1, 16. There's negative 16 and positive 1. There's lots of options. Remember, when you multiply to make a negative number, one of your numbers has to be negative. But we're looking for the special pair that will add to make this middle term as well. So which of these numbers in this list will add to make negative 6? These right here. So now I can take these two and rewrite them as the middle pieces of my problem. So I'll keep my x squared and my negative 16, but in the middle, I'll change this negative 6x into positive 2x and a minus 8x. It doesn't matter what order you write them in, you're still going to get the same answer in the end. Notice that positive 2x and negative 8x is still the same thing as a negative 6x in the middle here. So now let's group them. What can I take out of these two? We can take out an x, leaving me with an x plus 2. And let's group the last two terms. What can I divide out of those two? I would divide negative 8 out of those two terms. They're both negative. Negative 8x divided by negative 8 would leave me with the x. Negative 16 divided by negative 8 is positive 2. So my two factors are x plus 2 and x minus 8. Very nice. Now let's look at our third example here. Again, the a times the c. 3 times negative 2, negative 6. Now, what in the world would multiply to make negative 6? Well, there's negative 6 and positive 1, negative 1 and 6, negative 3 and 2, negative 2 and 3. There's lots of options, but we're looking for the special option that will add up to make the middle term of 1x. So what multiplies to make negative 6 and adds to make 1? These two numbers would add to make 1. So let's rewrite this term, or this guy, as the middle term in this expression here. So 3x squared. And then I'll just take this in this order, negative 2x, positive 3x, and negative 2 on the back stays. Okay? Notice this is still equivalent to the way it started. It's just rewritten with 4 terms. Now let's group. What can I divide out of these two? X. And then that would leave me with 3x minus 2. What could I divide out of these two terms? Just a positive 1, right? They don't have any other common factors. So I would then have 3x minus 2. When you divide by a 1, you don't change anything. So my two factors would be x plus 1 and 3x minus 2. Okay, so we have now taken a look at how do you turn a 3-term problem into a 4-term grouping problem. All right, so now let's look at our last method for factoring. What about difference of perfect squares? This is a common one to look at when you have 2 terms. So the difference of perfect squares, first thing you'd want to do is identify if you have each of the following. First of all, you need to have a difference. And you need to make sure you're looking at perfect square numbers. What does the word difference mean? It means you better have a subtract sign in that problem. A difference is what you do when you subtract, okay? Or you get the answer to a subtraction problem. A perfect square, remember those numbers that are square rootable nicely. So numbers that we know that are perfect squares, numbers that you can easily square root when they're inside of a square root. Like, what is the square root of 1? Well, that's just 1. Can you square root a number 2? Not nicely. How about 3? Nope. How about 4? Oh yeah, that's a number 2. You could square root what other numbers? Okay, so 4 is a, I'm going to rewrite this. 4 is a perfect square. What else is? 9, 16, 25, 36, 49. Remember, these are all just 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, so on. You dealt a lot of these, or you dealt with these a lot in geometry when we talked about right triangles and simplifying square roots, as well as in Algebra 1. So once we decide if we do have a difference and we do have a perfect square, then we can use it to factor into the two factors. One will be positive and one will be negative. So I have a lot of examples for these because for some reason these seem to kind of trip students up year after year. So let's see if you got this. So identify first if we have a difference. So notice in example 1, I do see a subtract sign. It is a difference. Do I have perfect square values for the coefficients? What number's in front of the x squared? 1. What number's at the back? 49. Is 1 a perfect square? Certainly. Is 49 a perfect square? Yes. That means I can use the difference of perfect squares pattern to help me factor. Now to do that, you must remember that because I only see two terms, that means the middle term, the x's, have canceled out. They were opposites of each other. That's the way that happens. So you might remember doing this in Algebra 1. Because they were opposites of each other, you would say, well, what do I have to do here to get my factors? I have to remember that one will be the exact opposite of the other. So what is the perfect square for the number 1, or 1 squared rooted becomes just 1? How do I multiply to make an x squared? X times x would make that happen. And how would I multiply to make a 49, understanding that 49 is a perfect square? How about 7 times 7? So notice that one's a positive 7 and one's a negative 7. The reason we only see two values here is that if I were to multiply this out, those x's would cancel each other out. They would basically make 0 x's in the middle. And that's why you don't see them. That's why there are no x's here. Okay, let's take a look at this next one. Number 2, are we looking at perfect square numbers again? Sure, 4 is a perfect square and so is 9. So if I was going to factor this, remembering that one's positive, one's negative, let's now do the square roots. To make a 4x squared, I'd have to do 2x times 2x. And to make a 9, I'd have to do a 3 and a 3, right? One positive and one negative so that I can multiply to make that negative 9 in the back. They are exactly opposites of each other. Now let's look at example 3. This is just like in a different order. The w comes at the end. How do I multiply to make an 81? 9 times 9. How do I multiply to make a w squared? W and w, and remember one's positive and one's negative. These were perfect squares. How about example 4? Do I see perfect squares again? Certainly. Let's look. How do I multiply to make a 16x squared? There's lots of ways. 2 times 8, 1 times 16, but we need to use perfect squares. So 4x times 4x, they need to be the same. What about the 25? 5 times 5. So one positive, one negative, that will cancel out those middle x terms. And let's look at example 5. Do I see the difference? Yes. Do I see perfect squares? 4 is a perfect square. What about 7? 7 is not a perfect square number. So this one right here cannot be factored. So just because it's got two terms and you have a minus sign in there doesn't mean everything in the world can be factored. That's an OR, by the way. So we need to be careful that we're watching for this pattern. Now the last two are really important. Sometimes you don't see this pattern right away. But remember, the very first method we learned how to factor was greatest common factor. The reason we do that first is because that's always the first thing you check. In this problem, there is a greatest common factor that we must divide out first before we can see the secret hidden pattern here. So what term can I divide out of both of these? What number can I divide both of them by? Well, I could take a 5 out, right? They're both divisible by 5. If I do that, if I divide them both by 5, then the 5x squared just becomes x squared, and the negative 20 now becomes minus 4, or negative 4. By pulling that 5 out, I now see a difference of squares pattern. Ooh, I see a 4, I see an x squared. X and x, 2 and 2, one positive and one negative, and that 5 that we took out right away is still a part of my factored answer. This is the factored form for this problem. We had to take the 5 out right away in order to see that pattern happening. Let's do the same thing here on example 7. Yes, there's two terms. No, they're not square rootable right now, but you know what? What if we were to divide something out? What can I divide out of both of these pieces? I can divide them both by the number 2, and they both have x's here, so I can at least take one x out from both parts. So if I take 2 divided by 2, I get 1. X to the third, divide out an x, I get x squared. What about negative 72? Negative 72 divided by 2 is negative 36. x, but I took him out. So this is the way it starts, by dividing out that 2x and just kind of placing it in front as the greatest common factor. And now my x squared minus 36, I now see the perfect square in there, and I can say that's x plus 6 and x minus 6. And the 2x that I took out right away, don't throw him away, he's a part of the factored solution. So this two-term problem factored out actually looks like this. So it was multiplied out to create this original example. All right, so now we've taken a look at all the different ways we can use to factor here up to this point. Now we'll be applying them in different situations in class. Okay, so be looking for the patterns, and I want to thank you for taking good notes today. Kincaid out.